Okay, today we're talking about Chapter 3, Section 4, Introduction to Functions and Function Notation. Alrighty, so we use functions all the time, whether you know it or not. Obviously, I mean you say about a lot of math, right? But today we're gonna talk about the ins well a short introduction to functions, the ins and outs, what the domains and ranges are. And starting down here, relation, domain, and range. So a relation is a set of ordered pairs of real numbers. Okay, so doesn't want to tell us too much, but let's move on. The domain, which we'll denote as D of a relation, is a set of all first coordinates in a relation. So the first coordinates, if you recall, right? If we write this like this, x, y, right? The first coordinate here is the x's. So the domain are all the x's. And then the range R is of a relation is a set of all the second coordinates. So it's going to be all the y's. Okay, so let's move with that knowledge, I guess. Moving forward, let's find the domain and range of these problems. And honestly, I guess this is just one of those where I don't necessarily have to actually do any computation, right? I can honestly probably snip this. So here we go. Example 1, finding the domain and range. So find the domain and range for each of the following relations. So A, we have G, which are the points 5, 7, 6, 2, 6, 3, negative 1, sounds like heights, 5, 7, 6, 2, 6, 3, negative 1, and 2. Okay, well the domains are going to be all the x values, right? 5, 6, and negative 1. 5, we have two sixes, but we don't have to write that twice, and negative 1. The range is going to be the y values, 7, 2, 3, and of course I want to say 2 again. Right? And of course that's shown here. And then the domain for B looks like negative 1, 1, 0. That's what we have here. And my range is 1, 5, and 3, what we see here. Right? It's just the x's and the y's. Okay? So reading the domain and range of a graph, right? So we looked at ordered pairs for example 1. For example 2, we're going to look at a graph. Okay? So example 2 reads, identify the domain and range of the graph of each relation. Okay. Well, looking at this graph, right? The graph is what you actually print onto the plane, right? The graph isn't this whole thing. The graph is just basically what you print onto it, just for clarification's sake. Anyways, the domain, it looks like it's going from negative 1 to 3, and we're including negative 1, and we're including 3. And we see that right here. The range going on the y-axis, right? The domain is horizontal. The range is, the domain is horizontal. The range is vertical. The range looks like we're going right here from 0 all the way up to 6. And that's what we see here, 0, 6. Over here, it looks like the domain, right, this is kind of tricky because you can only see the domain going from, right here, it looks like at like negative 5.5, all over here to looks like it's going over to 0. Okay, but these arrows at the end of these graphs indicate that it's just going on. So what that means is it's going to negative infinity, right? Negative quintillion. It's going there very slowly compared to how fast it's going up, but it's going there. Same thing to this side. It's going to infinity. It's going to quintillion all over here, right? Because I mean, if you just continue to draw this, it just kind of goes up, just keeps on going, keeps on going, keeps on going, and it'll eventually, get there, get to infinity, very slowly. Again, comparatively to the going up part. That's the domain. So the domain is going to be negative infinity to infinity. The range, right? Well, the range is, well, where does this graph exist vertically? What exists down here at negative 2 all the way to infinity. So you can kind of imagine, um, like just taking this blue line and just smushing it against the y-axis, and then you can see that it goes from negative 2 to infinity. All right. So let's see. Do we don't necessarily need that? We'll jump straight to this one. All right. So this is the big deal about functions is that we cannot necessarily have, well, we cannot have um, an x value that goes to a different y value. Okay, and so well, I guess yeah we can do this. Okay, so let's just go ahead and read what the definition says. A function is a relation in which each domain element, so each x, has exactly one corresponding range element. So each x has exactly one y. Okay, and that's it. That is a function. One x has to go to one y. Okay, um, we could have multiple y's being being on the receiving end of multiple x's, but one x can only go to one y. And so what I mean by that is look at A. We have 2 goes to 3, 1 goes to 6, 2 goes to square root of 5. Okay, well, we have an error there. Okay, we're saying 2 goes to 3, and we're saying 2 goes to square root of 5. All right. Well, this is obviously not going to be a function since they go since that 2. Hold on, let me fix my screen. Since that 2 goes to two separate y values. Okay, so A is going to be not a function. I don't know what we're supposed to put. Not a function. NAF. Okay. B, let's read B. B is 1 to 5, 3 to 5, square root of 2 to 5, negative 1 to 5, and negative 4 to 5. Okay, so we're all going to 5, but that's okay. We can have multiple y's being on the receiving end of x's. It's just that x is x cannot go to two different y's. So we do indeed have a function. Okay, we're just going to put an F for function. The vertical line test. Now this is when I was a student going through math courses. I wasn't. I didn't start out. I probably said this before. I don't know. I'm doing so many courses right now. But when I was a student and I was going through these math courses, I was not going to get a degree in mathematics. I was actually going for psychology. Um, and so whenever I got to this point, I'm just like, dang, this is pretty cool. Let's make the entire test. You know, let's make the entire final exam these problems because they're super duper easy. Unfortunately, they did not take up the entire test or final exam, and they won't in this class either. But the vertical line test is super easy, right? The vertical line test, you look at a graph and you say if any vertical line intersects the graph of a relation at more than one point, then the relation is not a function. So in the previous example, we determined if these points were a function, okay, by just looking at points of a graph. Now we're going to look at an actual graph, right, and then really drive the point home of why a was not a relation or a function rather. So the vertical line test C, we have this W here. We see we don't have any repeating. Like if these dotted lines, they're my vertical lines. Um, we do not have any sort of intersection more than once. Whereas here, well, we see we intersect more than once. All right, and so notice how we have a repeating x, 3, 4, and 3, negative 4. Well, that's kind of like A over here, right? We had 2 goes to 3, and then 2 goes to square root of 5. Right? So that's why we say that it is not a function, right? And now it is an equation. It is an equation. I mean, this graph does make an equation, but it does not make a function. And that's a very important distinction. And let's do some vertical line tests here. Let's see. Golly, how does this book have it? All right. A, B, C, D. What in the world am I looking at? Okay, so we'll snip all this down to C, I guess. Actually, let's not even snip it. Let's just go over it because I can't really snip this nice and neatly. Okay. So I mean, vertical line test, it's super easy. So it's not a big deal if I don't put it in the notes. I think, anyways. So it reads: use the vertical line test to determine whether each graph represents a function. Then list the domain and range of each graph. Okay. So looking at A, we have. Do we have the solutions? No, not really. Okay. No big deal. We can just say spitball, not spitball. We can just say these out loud. So A, do we have any repeating x's? We have -7, -3, yep. We have -3 is repeating, so A is not going to be a function. That was easy. Um, so B, we have just simply as V. This is definitely a function because we cannot create a vertical line that goes through 2 points, right? And the domain here looks like, the arrows, right? It's telling me I'm going to infinity. So the domain is -infinity to positive infinity. And my range looks like it's going from -2 down here on the y-axis all the way to infinity. C, okay, so C is obviously not a function because I can create vertical lines wherever I want to, right? And I'm going to cross in more than one place everywhere except for right here at the ends, but that's okay. Let's see. Yeah, let's get rid of that. This is just a jumbled mess. Is my eyes not working right? I don't know. Alrighty, well, whatever. Let me see. Is this D? I don't know. These are obvious. This is obviously not a function because we see we have a vertical line going through multiple places here. This is a function, okay, because we can create vertical lines, but we're not crossing it more than one place. And it looks like my domain is going from -2 to +2, and my range is going from 0 to infinity. I'm sorry, so you say infinity, 0 to 2. And this one is, I guess that's E, is obviously not a function because we can cross it more than one place. And I guess this is F. This is also not a function because, well, we can read that every point has the same value. Okay, we have multiple x's, right? Not just 2 this time. We have multiple x's, and they're all at -3. Whew. And that was a mess. I think it looks better in my textbook. I don't know. So finding the domains of functions. So the domains of functions, you're gonna be finding the domain of functions. Oh, man, honestly, until you're done with your math courses. Um, let's see, I think I can word this a lot better. No. Okay. So example 5. Let's jump to example 5. Trying to find the domain of this function. So I obviously skipped over the text there because I wanted to explain it more in my own words as we go through this. Alrighty, so I know that and your parents know this, right? There's one rule I think that everybody that's ever taken a math class can remember. That rule is you cannot divide by 0. Okay, so if we cannot divide by 0, then that tells me that is going to be the part of a function that is the part that I'm going to say cannot exist. So looking at this particular problem, my numerator there, okay, so let's just go and write this. My numerator can be anything. This x can be anything. It does not matter what that x is. Okay, the x can be -5. The x can be negative pi. It can be positive pi. It can be pi cubed. It does not matter what that x is because it doesn't matter what the numerator is. What we are concerned with is this denominator. That's the only thing we're concerned with. When we're asked to find the domain, we're only concerned with this denominator. Okay. Well, what can the denominator not be? Well, it cannot be a 0. If it's a 0, it is undefined. So what I must do, I must take this denominator, and let's move this up to the top left. I must take this denominator, and what I'm going to do is I'm going to equate it to 0. And yes, you do this with every single fraction like this. You take the denominator and equate it to 0. Okay, well if I equate it to 0 and then I solved, I have x equal to 5. Okay, so when I put 5 in for x, I get 5 minus 5 is 0, and then this entire problem is undefined. Okay, so this is where a lot of the confusion might set in as a student. And again, for me, when I was taking the course and I didn't really pay attention, I didn't care about math, this is where some confusion set in for me. So I solve the denominator, I get x equals 5. Okay, but what that's telling us is not that x is equal to 5. It's telling us that the denominator can be everything but 5. So what I'm essentially doing is calculating the restricted value. Okay, so I'm not solving this problem. I'm just figuring out what I can't use. So I know I cannot use 5, but I can use every other number, right? I can use every other possible number in the universe except for 5. So this tells me the domain of this particular problem, okay, the domain is going to be from negative infinity to a positive 5, unioned with 5 to infinity. Now this notation real quickly, um, I'm using a, let's see, I'm using a parentheses, right? Because that means I cannot use it, right? I'm getting as close to 5 as possible without actually touching 5. So I'm going from negative infinity to 4.999999999, and then I'm going from 5.00000000001 to infinity. I am not touching 5, okay? And then this u here means basically just a union, that I'm putting both of these intervals together, okay? Now, in this particular case, these are intervals and they are not points on a graph. And so that's the point, and there is an important distinction to be had there, and you'll usually have that important distinction based upon the context of the particular problem or solution. Next up, we're going to have function notation, and we're just going to go ahead and snip this whole thing. Again, one of those problems is pretty easy. So function notation goes like this. We have y is equal to mx plus b. We can essentially change that y into an f of x, all right? And we read that as f of x. So it can be essentially be read as f of x is equal to mx plus b. What does f of x mean? Well, f of x means the function at x, right? What happens at the function at x, right? And you know how that we use different letters for variables, right? We've used x, y, I'm pretty sure we've used like a, b, m, n, things like that. We've used different letters for variables. We can also use different letters for function names, right? So f is usually the lowercase f is usually the name that we call functions, right? That's kind of the default, like x. And then g, h, and of course we have them as uppercase letters. Well, what this f of x means, again, means a function at x. What happens at x? Well, what you do is you're going to plug the x value in and you're going to get that value. That y value is the same thing as y. Okay, so in a sense, y, let's see if I can maybe do this. I don't know if I can't do it. I can't write that small. So in a sense, y is the exact same thing. I mean, I say in a sense. I mean, it is. It is the exact same thing as saying the function at x. Okay, you can also think of it as a coordinate as x and then the function at x. Okay, they are indeed interchangeable. They're essentially the same thing. It's just saying what happens when I plug an x value in, the x value being whatever this particular x value is being said, and then that gets my y value. So let's look at the example down here. We have for the function g of x equal to 4x plus 5, find g of 2. Well, what we do, see, notice how the 2 here, g of 2, we have g of x. The 2 replaces the x. So in the problem, you replace the x with a 2. So you'd say 4 times 2 plus 5, which is 8, plus 5 is 13, and we see that here. Same thing here, g of negative 1. Well, this negative 1 is replacing this x right here. So this negative 1 is going to replace this x right here. So 4 times negative 1 is a negative 4. Negative 4 plus 5 is 1. And then lastly, g of 0, same thing. You plug 0 in for x. 4 times 0 is 0, plus 5 is 5. All right. That is how you evaluate functions at, well, just evaluate functions, honestly. Right. This one is not any harder. It's just, a little more computation, but it's not anything that you cannot handle. All right, so let's actually make this a little bit bigger since it has its own page. Right, so same thing as the previous example. Nothing too difficult. You just take this value here, this 4, h of 4, h of 0, h of negative 3. You take that value and then you replace the x with it, right? 4 squared is 16, minus 3 times 4, which is 12, so 16 minus 12 is 4, plus 2 is 6. We see that here. H of 0, 0 squared is 0, minus 3 times 0 is 0, 0 plus 2 is 2. And then negative 3 squared is a positive 9, right? Negative 3 times negative 3 is a positive 9. Minus 3 times a negative 3, so it's going to be plus a 9 again. So 18 plus 2, which is 20. Right? Evaluating functions, uh, it's really you just plug things in and go. And I know many of you are probably going to use a calculator for this because you're kind of scared. You're not confident enough with your mathematics. And I only say that because I have students in pre-calculus and calculus that still do 7 times 4 on a calculator. But I mean, I say this, but I mean, try to do some of this stuff in your head, and I promise you, you're gonna be churning these out quicker than you think. All right. And then lastly, because we're not going to use a graphing calculator in here. Lastly, we're going to talk about evaluating a function from a graph. Okay. So looking at a graph, and we will just go ahead and write this one out. Looking at a graph, I mean, it behaves pretty much like you would think it does, but you might need a push in that general direction to understand. All right, so what do I mean by that? Well, if we do it once, I think you'll understand. So in the previous two examples, we replaced the x with whatever this value is right here. Right? In this particular case, we have negative 2, 1, and 4. And this time, what we're going to do is we're going to go to that part on the x-axis and find where the graph intersects, or not necessarily intersects, but where the graph is. Okay, so what do I mean by that? Well, g of negative 2, we're going to go over here to negative 2. We create a line there, and it looks like that blue line is up there at 4. So we would say a is going to be 4, positive 4. Okay. Let's do g of 1. We're going to go over here to 1 on the x-axis. It looks like we crossed there at negative 2. Right about here. So it looks like uh, g of 1 is negative 2. And then C, we have g of 4. Okay, so let's go over here to 4. That's not a good straight line. Let's try that again. 4. And it looks like we are crossing here at negative 9. Negative 9. Okay, and that's how you evaluate functions looking at a graph. And like I said, we're not going to be doing the graphing calculator part, so I believe that does conclude today's lecture. And that's it.